Thanks for joining this talk. My name is Musa Marcusso. I'm from BOSCH Research from the Robotics Systems Department in Leiningen. And I'm going to talk about, so very close to the ROS-Con talk that I did as well, and on the Python library I've been working on to allow scripting and rapid prototype of Gazebo simulations. So a short introduction is just what would be the ideal process when you're building your own simulation to test your applications. So it's like a very simplified thing. Let's say you have you want to build your model, so you have your geometries. Hopefully, you have your meshes as well. You have you know how your kinematics chains look like. You know where you put the joints. You have parameters in sense like masses, moments of inertia, the friction, some magic numbers like bounce coefficients maybe, and then you take all of that and then you write your own SDF or URDF. Usually, robot descriptions are in URDF if you want to use that with ROS applications. And it's in XML format, and then you get your Gazebo models. And then when you have a certain number of assets, you have some idea of how the environment is going to look like. You place those in the simulation. You configure a physics engine, and then you write an SDF describing all of that, and everything works. If life was that beautiful, it would be amazing. But the thing is that a simulation is a very complex, like developed simulation is very complex. So very often the simulation itself is not the end goal of your application, right? So you want to use the simulation to test your algorithms, but it's not the final target for whatever you're developing. So very often people don't have that much experience building simulations, so they might run into many issues that I listed there. Some of them involving things that are not necessarily related to the physics, which is, for example, you have your meshes, and then if you ever got the magical task of converting those beautiful CAD files into meshes that you can use without which are usually not low poly and are going to make the contact physics a little crazy. You can see how it can take a while to find a way to export those meshes in a format that you can open in Gazebo, and also sometimes you have the problems with materials that sometimes you have a Blender format where the normals are flipped, so you cannot see anything Gazebo of the sun because the normal should be in the other way. Sometimes you have wrong physics parameters because you might not know everything about your environment. Sometimes you might have issues, for example, if you place a very tiny sensor on top of your very large link of very large mass in the robot, that might lead to instability as well. So you have to learn how to adapt those make some design decisions to make that possible. And sometimes you have to, and usually what you do is you change something in your configuration, then you open Gazebo, you see if everything explodes or not, and then you close Gazebo, change something, and go on debugging that. The same thing for the world. If you mess up with the physics engine configuration, if you don't use the default ODE parameters, you might also see some funny things happening. And that is also because the complexity of a simulation can be underrated most of the times. And that if you're not really looking into having the simulation being your end goal in your project, that can be a little frustrating. So some of the application-dependent difficulties that I listed is, for example, if you want to test your navigation system in the world, and then you just want to add some variations in object placements, but you don't want to write several similar versions of the SDF file for the world file. This can be also a little bit complicated to manage that kind of information. So how do you script world layouts instead of having static world layouts, which make it more flexible to change and automate how the environments are going to look like? And also we have event-based actions, which can be very, very interesting if you want to test some behaviors. Another thing is that usually robot descriptions, since you're talking about ROS here, robot descriptions usually are written in URDF, but for simulation purposes, SDF is much more powerful. The problem is that for example, one of the problems that we had that might lead to people not choosing SDF to write the robot description, so their physics parameters are described more in more detail, is strongly related also to the proposal for SDF 1.7, because it's harder if you have everything described with respect to the model origin instead of being relative to another one. So if you start modeling a manipulator, you soon run into trouble. And the conversion between these formats is not that easy because of also those differences. So if you don't use SDF, you don't use the full potential of your simulation. That's basically it. So the approach here I've been developing inside the development of this Python library is a technique from gaming development called Procedural Generation. So allowing you programmatically controlling and creating your simulation environments. That allows rapid prototyping of simulation scenarios. You have to have abstractions or simulation entities. So if you have links, joints, lights on their simulation, you need to have like a counterpart on your library too, so you can export to the SDF format that is necessary for Gazebo to understand it when you finish your configuration. Scripting of Gazebo simulations, which is very interesting, especially if you're talking about trying to repeat a simulation over and over again, let's say machine learning purposes or reinforcement learning, for example. And having that tool is actually really interesting. Extending templating option for robot descriptions, I'll talk about that a little bit later. But right now, I think everybody uses Sacro for templating robot descriptions, but there are other options that might be interesting if you want to make more complex templates. And improve the conversion between RDF SDF, which might be deemed very useless as soon as SDF 1.7 comes out, but it's still very useful in the sense where when you want to just have a very intelligent way of stripping all of those Gazebo parts, you write your whole description in SDF, and then you put just the essentials on the URDF file, and then you have a little bit more clear what is happening during these conversions between formats. So the package is called PCG Gazebo packages, and it's mainly made of the generators, which are model factories, model group generators, or generators, which use kind of engines to compute the placement of the objects in the world, for example, or compute the dimensions of a model that you are going to dynamically generate. Simulation, the abstractions that I was talking about, the links, joints, sensors, everything that Gazebo can simulate has to be modeled in here as well. Parsers, which is is basically the communication with Gazebo. With everything you do in the Python side is in the end is going to be all converted to some kind of XML file in SDF, and so that you can load your simulation Gazebo. So this part is one very important part, especially template processes. So Sacro is also in there, but also Jinja. So Jinja is a very powerful templating format that is very easily extensible. So you can write macros and more parsing engines within it. So and the PCG contains some of them to, for example, find your Python, your ROS package where your meshes are, because usually you don't have those paths. So it makes it a little easy. And Task Manager, which is basically just to allow your script to also start Gazebo, run some tasks, and set up like communication with some topics, so you don't have to open externally on a terminal. So some features that I'm going to show in video format, so it's fun. One thing that you can open a Jupyter Lab, and then you can have a full list of all the Gazebo static models that you have on your resources path. You can open one of them using their name tag and just, for example, visualize collision and visual geometries, and you can see the origin of the model, so you can check if everything is correct, if the mesh is correct, if your origin is correct. You can also inspect the SDF directly in that case. And you can see also, you can directly access the parameters of this SDF. So you can actually modify something like in this case, the mass of this backpack, and then export the SDF again, or spawn it to Gazebo. So you don't need to regenerate this SDF file over again. So next one is just one example on how you can make some fun tests in Jupyter Notebook with Gazebo. So you open Gazebo, in this case, it's going to create a box model, but every time it spawns the box model, is going to change only the friction coefficient of the surface of this box. But I don't need to regenerate the whole model again. So each one of the boxes has a different coefficient, and I apply some force just to check how these forces how the friction coefficient changes are going to affect my simulation. The next one is another option to generate your robot description. In this case, would be actually writing it in Python. So you can generate all the links and the joints and the sensors and everything else using the PCG library, and you can connect them. You can connect them in the model as you would in the SDF format, but the good thing is that once you do that, you can actually convert it to SDF or to a static Gazebo model or to URDF, so you have all the options that you want if you want to use this with a ROS topic or not. And in this case, I generated one first mobile base with the wheels, and basically I just added some new sensors upon the camera, an IMU, and I respawned a new version of it, so basically not really needing to have like two different URDF configurations, for example, for your robot description. The next one is the model factory. So if you want to generate very basic, like single link models in your simulation, which is usually very good to just populate your world, you can do that with the package too. So these three shapes on the floor, they are basically polygons that you can choose to extrude the whole polygon or just the border. So you can basically generate walls inside, which is very, very nice for navigation purposes. And you can generate all the primitives, like the spheres, the cylinders, the cubes, for example. You can give the engine the lambda function. So every time you regenerate, you call this model, it's going to regenerate those parameters, basically. So you can just respawn it over and over again. It's going to shape it differently. And for meshes, the interesting thing is that if you have a mesh and you just want to generate a single link model of this mesh, you can tell the PCG either approximate the collision geometry to a cuboid or to a sphere, to a cylinder, and it computes also the mass. You give a mass to it, and then it computes the moments of inertia according to your choices, and then you can just spawn like one mesh as one model inside the simulation, dynamic or static. So the other thing is related to how to interact with robot descriptions, both existing ones and the new ones with Jinja. So this one shows like opening the UR5 from the Xacro file that comes with the repository on GitHub, so I can just inspect how it looks like, and I have access to the joints, the links. If you want to change anything there, you can also change it directly in Python. And in this case, it shows I rewrote the Kabuki model in Jinja, and it produces an SDF file. So it's a purely Gazebo model of it. So I can also inspect the meshes. This is a collision mesh, for example. And later on, what I do is I start Gazebo using the task manager interface and spawn the Kabuki model. I read the ROS topics, because every time you create the simulation, there is a procedure to randomize the ports for ROS master, because this is still ROS1. I'm still not that cool, but it randomizes the ports for ROS master and Gazebo, the Gazebo ports, so you can actually parallelize Gazebos and ROS masters, so you can actually open as many as, well, before your computer melts like mine. I melted 3 so far. Yeah. But then the other thing is that it also has a very basic interface, so you can, for example, I run there the ROS topic to just tell the kabuki to run in circles, and you can do this all in Jupyter or in a Python script, which is pretty nice if you're wanting to repeat the simulation, or if you want also to have it just in a format that you can actually get all the data and modify the models on the fly. So another thing that is one of the main features that was actually what motivated the development of this package was how do you generate worlds where you can actually pick and choose like what you're going to randomize in the world, like you're going to do some random placement of things with collision checks, of course, because otherwise when you start your simulation things kind of they are thrown off from each other, and that's not what you want. So let's say this is a model of the Smart Life Lab at the Bosch Research Facility. And we have the original setup, how it's originally thought to be. So you can also generate this in PCG, like you just give a fixed pose to every object, and it generates your world file. And the good thing is you can also give constraints. So you have, like, for example, a model that is not completely on top, like the origin of the model is not really the floor, for example, which can happen. But then you can give a constraint to put to make every object touch the ground plane or some other geometry. So everything will be corrected to be on the ground plane automatically, so you don't have to deal with that problem. So let's say I want to randomize a little bit. You can randomize on an existing world like that one, but in this case I wanted to show just, in this case, what I made 3 workspaces in this room: living room, kitchen, dining room. And I told the PCG engine that in each one of these rooms, certain model assets should be generated randomly, should be placed randomly with collision checks so they don't overlap each other. So basically, what happens, I put dining room assets to be generated in the dining room area. Same thing with the kitchen, same thing with the living room. So you can have this as a Python script, or you can actually do a YAML file and just call it over and over again, and every time the world is going to look different. So you can generate a set of environments with very little effort, which manually would take a long time. So, and you can also, like the models, you can also visualize the collision and visual geometries of the world, so you can also open them before opening a Gazebo, because then the simulation is already running. When something is wrong, then it's too late. And one thing that is also very interesting for maybe navigation systems is that once you have this world file or the world configuration, you can actually run ray tracing and just get the occupancy grid of this world that you have. And you can also exclude, for example, if you want to say, in the grid map, I will assume that the handbags, the shoes, and the skateboards were not there before, so I want to just hide them from the grid map so that the robot has to find them like as a surprise when it's running around the environment. So it's you don't need to run the simulation first to generate the grid map, then run it again, use that grid map as a reference. It's just nice to have. And so the PCG is basically one way not only to allow you to script your simulations, but also it allows you to never touch the XML files ever again. It is, in my opinion, a very good thing. The scripting, it generates the assets. You can dynamically generate models. I didn't put all the features there, but you can also dynamically generate models, model groups. So you can generate whole model groups and spawn them all together. And the one thing that I like very much is being able to use Jupyter notebooks to do your experimentations and slowly build up your simulation. You can do inspection of your models, and the conversion between SDF and RDF makes it really much easier to really have the power to choose if you want to concentrate on having a very reliable Gazebo model, or if you want just a simple RDF that's going to describe your kinematics, so that makes it easier. And it's available on GitHub under Apache 2 license. And if you have any questions, I'll be happy to answer them.
So Any questions? We have time to do some questions if you have.
Just a very quick one. How would you say it compares the Jinja templating scheme with respect to Chakra for URDF5?
I would say Jinja has already some things that I really like, as simple as for loops, which for me is really useful. But you can also use the same data structures as in Python, so dictionaries it can also be useful. I like the way that you can use a much more flexible way for writing your macros. So it's not, how can I say? It basically has more functionalities to do with the data that you're dealing with. So you can pass a whole dictionary with the parameters to configure that robot description and generate the template out of it. And I think Xacro is faster, that's for sure. It's faster to generate on the fly, the robot description, but the amount of functionalities is not that great. I think Jinja is actually, you have more freedom to build very complex robot descriptions if you want to.
Okay, other questions? No. Then thank you very much for your presentation.